In this video, we'll take a look at optimization. And all optimization is finding max or minimum values in an applied context. But as you read through the textbook and as you read examples, you're going to see they fall into roughly two camps. There are nice examples where you're just given an equation and you're told you need to find the max, you need to find the min. And then there are, I would say, trickier examples where you're not given an equation and you need to figure out what you're maximizing or minimizing on your own. And I'll start with one of those trickier examples. This is a venerable classic. The old building a fence example shows up probably in every calculus textbook that's been published in the last 100 years. You are enclosing a rectangular region with a fence. You have 800 feet of fencing, but one side of the enclosure will be a river that does not need to be fenced. What is the maximum area of the pen? So it's often, although not always, helpful to draw a picture just to try to get what's going on clear in our head. We have a river and we have a pen. And because the river is providing a side of the pen for us, our pen only has three sides. This rectangular pen has an area. We want to maximize the area. And the textbook, there's no one size fits all method of doing problems like this. The textbook lays out what I consider to be a pretty credible sort of guideline. Drawing the picture was step one. Labeling relevant quantities is step two. So we want the area of the pen, and we know what the area of a rectangle is. It's the length times the width. So let's call that the width, the vertical distance on my paper, and the horizontal distance I'll call the length. And I want to maximize the area. Um, and I guess this is sort of this equation which I wrote down is step three of the textbook's method. I selected a quantity that is to be optimized and I constructed a function. Step four says that if the function constructed in step three has more than one variable, we need to get it down to one variable. That is, if we want to maximize the area, we're going to ultimately be taking a derivative and setting it equal to zero. But we don't know how to take the derivative when we have a variable L and a variable W. It is a problem that we have two variables, so we need to somehow get rid of one of them. And we go back to the problem and we ask, is there a relationship between the variable L and the variable W? And we see the number 800 show up. And this 800, this is the amount of fencing we have. In terms of the variables L and W, how much fencing is there? Well, we need W fencing for the left side. We need L fencing for the top. We need W fencing for the right side. And this ought to be 800 feet of fencing in all. So we have the relationship 2W plus L equals 800. And the purpose of all of this is to eliminate one of these variables. L is 800 minus 2W. Just taking the equation we had and subtracting 2W from both sides. If we take 800 minus 2W and plug it into the area formula, the area is 800 minus 2W times W, or 800W minus 2W squared. So in practice, we're usually looking for an absolute max or an absolute min. And absolute maxes and absolute mins, the method we have for finding them assumes that we're on a closed interval. And sometimes that's not true, and we have to improvise a bit. Here it is true. W, well, it's sort of true. W can be between 0 and 400. In practice, W can't really be 0, or there wouldn't be sides. And W can't really be 400, because if W were 400, then you'd be using 400 plus 400 is 800 feet on the sides, and you wouldn't have any feet left for the upper side. So, sort of, this is actually an example of what I'm talking about. Really, W is on an open interval. I'm going to pretend that W is on a closed interval so that our method works. So, to find an absolute extrema on a closed interval, we take the derivative and we set it equal to 0. We find the critical values. The derivative is 800 minus 4w. This always exists, so there aren't any critical values due to the derivative not existing. There is a critical value due to the derivative equaling 0. And that critical value is at 200. So we look at the area at 0, at 400, and at 200. Well, when we stick 0 in, we get 0 for the area. When we stick 400 in, we get 400 for the area. We get 0 for the area. Sorry about that. When we stick 200 in, we get 80,000. So we're looking for the maximum. Is it 0? Is it 0? Or is it 80,000? I would say that it is 80,000. So the max area we can enclose is 80,000 square feet. And in terms of dimensions, W is 200. So the width is 200. The length we can figure out from this formula, 800 minus 2 times W. The length is 400. And this generates our maximum area. And I mean, every example in the textbook is pretty different. That's typical for this section. I think I'm just going to do this one video and then you will read the other examples in the textbook.